All right, so today I wanted to start a new part of the course, and this section is on beams. And I brought my little rubber beam because we're going to talk about beams for the next few lectures. So one of the things about beams is they carry transverse loads. So say if I support my little beam like that, I'm applying the load like this to it, okay? So transverse loads. And if you look at my little beam here, I'll pass it around so you can play with it. So if we load it like this, what you're going to see is that these straight lines here, they rotate. Okay? And as they rotate, they get closer together at the top and they get further apart at the bottom. And that means the top's in compression and the bottom's in tension when I do that. Okay? So obviously if the top is in compression and the bottom's in tension, there's some line along here that sees neither tension nor compression. It sees no stress at all. So one of the things we want to do is figure out what the stresses are in the beam. Okay? And the stresses are going to depend on the moment at a particular section. So we need to figure out the moments first. And we're also going to figure out the shear forces. So when say I've got my beam like this, and I'm putting a load on it like that, you can kind of imagine if I chopped out a little element here, it would see a force like this and a force like that on the two sides, right? There'd be one this way and one that way, and then there'd be corresponding shears on the top and bottom. So there's going to be shear forces developed along here. There's going to be bending moments inside the beam, and the shear forces are going to relate to the shear stresses, and hello. And that interrupts the video, you know. We're going to have to edit that out. So the bending moments relate to the normal stresses. So when I say that there's compression or there's tension along the length of the beam, that's going to be related to the bending moment. So the first step is we need to figure out what the shear forces are along the length of the beam and what the bending moments are along the length of the beam. Okay? And then next time, hopefully, we're going to relate that to the stresses. All right? So I'll pass it around so you can get to play with it and just mush it around a little. Okay? So let me write a little bit on the board. So the idea with beams is that they carry transverse loads. So if this is my beam here, we'll have a couple little supports at the ends, and we'll talk a little bit more about that later. That's my beam there, and it's got some load P on it like that. Okay? And we're going to figure out the shear forces, the bending moments, and we're going to look mostly at the normal stresses, and we're also going to look at the deflections. Okay? So I have some examples of applications for the beam bending. So these are applications that are mostly in material science. So you know that I work on materials that have a cellular structure, honeycombs and foamy kinds of things. And when we deform them, they deform by the edges bending to a large extent. You know, in certain circumstances, they don't always bend, but mostly they bend. And so if you want to calculate, say, the Young's modulus of these materials, what you need to do is calculate how much the cell walls bend. And if you can calculate how much they bend for a given force, you can back out what the Young's modulus is. So these cellular solids are some examples of materials that you can calculate the properties of by looking at the bending. So here's another set of examples. We talked about the bone a little bit before when we talked about the principal stresses. This is a micro CT image of the bone there. I forgot to put this thing in. Hang on a sec. Let me shove that in there. Whoop. There we go. There we go. And then this is what happens when people get osteoporosis. This is vertebral bone, and that's vertebral bone in a 55-year-old woman. It has a relative density, which is the same as the volume fraction of solids. So this thing here is the density of the bone divided by the density of the solid. That's the same as the volume fraction of solids of about 17%. And you can see this is a much older woman, 86. And the relative density, or the volume fraction of solids, is about 7%. So that person's lost over half the bone in their vertebrae. And you can kind of see how the bone here is all nicely connected, like each one of these little struts and beams is all connected to its neighbors. And you can kind of see, especially in here, the struts are no longer really connected. And it's not too surprising that if you lose bone mass like that, that you are at a greater risk of fracture because the strength of the bone drops off. So one of the things we had looked at was how you can use the models for the foams that are based on bending to say something about the properties and the modulus and the strength of the bone. Let's see. So here's another example. Tissue engineering scaffolds also have a structure that looks a little bit like a foam. These two here are kind of more honeycomb-like, and this one here is more foam-like, and this one here has been made by a selective laser sintering process, a sort of rapid fabrication process. So the same sorts of models you can develop for the honeycombs and the foams, you can apply to the tissue engineering scaffolds. And it turns out when you put cells on the scaffolds, the cell behavior, like the biological cells, if you put fibroblasts or you put osteoblasts or something, you put some biological cell on, their behavior can depend on the mechanical properties of the substrate they're on. So people who do tissue engineering are also interested in the properties of the scaffolds, the mechanical properties. Another application of bending that's relevant for material science is in atomic force microscopy. And the way the AFM works is there's a cantilever beam here that has a little tip, and that tip is scanned over the surface of the material, and that beam bends, and depending on how much it bends, there's a laser here that you then sense over there, and you can detect the surface by the bending of that little beam there. Okay, so that's another application there. Another application in material science is when you have thin films on substrates. So say you're making an electronic device or a magnetic device, you often have a substrate and then you deposit various layers on that substrate. If those layers have different coefficients of thermal expansion and there's a temperature change, then you can induce bending in the thin films on the substrates. Okay, so that's another example. Another example is just in sporting equipment. So if you look at the design of downhill skis, they're designed for bending, for a certain bending stiffness. Or if you look at, say, pole vaults, you know, the pole vault runners, they have their pole, they run along, they stick their pole in the ground, and it bends so much. That when it's bending like that, it's storing strain energy, and it's that strain energy that then gets released that gets them over the pole at the top. Okay, so there's interest in bending for designing sporting equipment. And then obviously in civil engineering, designing structures, bending is a big part of designing structures. So let me just put some of these applications down here, and then we'll sort of move on to the more technical details. Okay, so there's lots of applications for beam bending, even in material science. And what we need to do is we need to find, first of all, what the support reactions are. Then we're going to figure out the internal forces and moments, relate those to the internal stresses, and then get the deflection. So there's a sort of series of steps we're going to work through here. off. Get rid of that. So in order to figure these things out for the beams, there's just some notation things we need to go over first. So one is just the end supports. So there's various types of end supports that you see. So one is a roller. So if I draw that, that's the roller. And if we have x and y directions like that, the roller just means, like, say my beam was on top of it like that. It's free to slide back and forth in the x direction, so there's no reaction in the x direction. And it's also free to rotate, so there's no moment there. And the only reaction we have for a roller is a reaction in the y direction like that. Okay, it can't go up and down because there's the ground there. Okay, another type of end support is a pin. So say that's my pin there. And for the pin, there's going to be a reaction in the y direction like that, just like for the roller. But we could also have a reaction in the x direction. It can't slide back and forth. It's prevented from sliding like that. So there's a reaction in the x direction. But because it's a pin, we could still have rotation about the pin, so there's no moment there. Okay. And then another type of end support is a fixed end. So say we have the beam kind of built into the end here, to the wall. If it's built into the wall there, it can't move up and down. It can't move from left to right. So we can have reactions in the x and y direction. But if it's built in, it can't rotate either. And if it can't rotate, then we can get a moment at the end there too. Okay. Okay. So those are the end supports. There's also a couple of sort of names for beams that are supported in certain ways. Say I have a beam that has a, a pin at one end and a roller at the other. That's called simply supported. So if I say a simply supported beam, it just means there's a pin at one end and there's a roller at the other end. And another type of beam is called a cantilever. And a cantilever just means it's fixed at one end and it's free at the other end. Okay, so those are just kind of notation things.